Dear students, will prove a result on projections in this lecture. So, let us see the statement of this result. Let P be a projection, P be a projection on Banach space B, on Banach space B. P be a projection on Banach space B. If M and N are range and kernel of P, then if M and N are range and kernel of P, then B can be written as direct sum of M and N. Proof. So before we see the proof of this theorem, let me explain you what is the meaning of the fact that B is direct sum of M and N. So it means that every vector, say x in B, can uniquely be written as M plus N, where M belongs to M and N belongs to N. So every vector can uniquely be expressed as sum of elements of M and N. Here M and N are unique, such that M belongs to M and N belongs to N. So from linear algebra, you may be knowing that to prove that B is direct sum of M and N, we need to prove two things. First, B can be written as M plus N. So what it means, every vector in B can be written in the form M plus N, where M belongs to M and N. And for uniqueness purpose, we have to prove that M and N have no vector in common except 0 vector. So M intersection N is singleton 0. I would like to modify the statement little here. In addition, we can say that M and N are closed linear subspaces. Further, so this is an additional part which I will add here. Further, M and N are closed linear subspaces of B. Further, M and N are closed linear subspaces of B. Proof. So proof is simple. I begin the proof by defining M as, or by specifying M. M is range of P and it consists of all images of all vectors in B. N is kernel of P, n is kernel of P, and it consists of all those vectors of B which get mapped to 0. Okay, so we'll prove this in some parts. Again, let me recall the definition of projection. So P is projection on B, means that in last lecture we have seen the definition of projection. So P from B to B is projection, means that it satisfies three properties. First, P is linear. Secondly, P is continuous. So it is an operator on B and it is going to be linear and continuous. And defining property of projection is that P square is equal to P. P square denotes here P composition P. So that is equal to P. Okay. So M and N are range and kernel, and we have to prove that B is direct sum of M and N, where M and N are closed linear subspaces of P. So first we will write B as sum of M and N. So this is the first property which we are going to prove. Let Z belongs to B. Then we can write Z as adding and subtracting the vector Pz. Z plus Pz minus Pz. This I'll write it as Pz plus Z minus Pz. This is equal to Pz plus Iz minus Pz. Let me specify the notation. I denotes identity operator on P. So I is function from P to P such that I of Z is equal to Z. I of Z equals to Z. So this is identity operator and Z I am writing as Iz. Pz plus I minus Pz. Okay. This, so if you observe, where is Pz? It is in clearly the set M. It is clearly in the set M, which is range of P, and N, we can, this vector is in the kernel. So let us verify this. Clearly Pz belongs to M. Also P of I minus Pz, let us simplify this, it is going to be P of Iz minus Z, that is Z minus Pz, and by using linearity of P I can write this as Pz minus P of P, that is P square of Z, which is equal to Pz minus Pz. Why is it? Because P is projection, so P square is equal to P. So P square of Z is same as Pz and it is equal to 0. So I minus Pz belongs to kernel of P, that is N. Pz belongs to M and I minus Pz belongs to N. Why I minus P Z belongs to N because its image under P is 0 and kernel consists of all those vectors which image is 0. Okay, so I minus Pz belongs to N. Thus we have written an arbitrary vector in B as sum of two vectors. First vector is in M and second vector is in N. So this proves the fact that B is sum of M and N because Pz belongs to M and I minus Pz belongs to N. So every vector in B can be written as sum of two vectors where first vector belongs to the set M and second vector belongs to the set N. Then we will prove that M and N are linear subspaces of B. So this part, it is fairly easy to prove that range and kernel are linear subspaces of B, and from linear algebra you must be knowing. So this part is going to be a trivial. So I am not going to supply proof for this simple statement. I will simply put it here that M and N are linear subspaces of B. You try to prove this. It is a fundamental result from linear algebra that range and kernel are always linear subspaces of any linear transformation. Third is M and N are closed linear subspaces. So they are linear subspaces, but the important point is that from analysis or topological point of view, they are closed linear subspaces of B. Closed linear subspaces of B. Subspaces of B. So proof of this result. First I am going to prove that N is closed linear subspace of B. N I can write as set of all those vectors in B which get mapped to 0, and this is nothing but inverse image of the function P, the inverse image of vector 0 under P. So it is P inverse singleton 0. Any finite subset in any metric space is closed. So singleton 0 is closed. Okay. And P is continuous. So by definition of continuity, inverse image of closed set is closed, as singleton 0 is closed as singleton 0 is closed in B and P is continuous P inverse of singleton 0 which is equal to N is closed in B. So we are done with this, that N is closed linear subspace of B. Now what remains to be proved is that M is also closed linear subspace of B. M is closed linear subspace of B, and in order to prove that M is closed linear subspace of B, we have to use the result which we have proved in the previous lecture. So M is set of all images of all vectors in B, and by the result which we have proved in previous lecture, we could write this as Z such that Pz equals to Z, because the result which I am referring is this: since Pz is equal to, or better let me put it in this way, since Z belongs to M, if and only if Pz equals to Z when P is projection, and M denotes range of projection. So this result we have proved in the previous lecture, and that we are going to use here. Since Z belongs to M, if and only if Pz equals to Z when P is projection. Now this result I could write it as Pz minus Z, or let me put Z minus Pz equals to 0. Further simplification would be Z Iz minus Pz equals to 0, which further I could write it as Z such that I minus P Z equals to 0. This I can write it as I minus P, it is inverse image of 0 vector under the map I minus P, and as we have seen 0 is closed in B, and also I minus P is continuous. Why is it? Because I and P are continuous. So inverse image of closed set is closed, and for the same reason which we have seen for N, this is going to be the closed subset of B. So as earlier, or with the same explanation, I could write I minus P inverse 0 is closed, and this is nothing but M is closed subset of B. It's closed subset of B. So far we have proved these three properties. Now last property which we are left with is this: we want to prove that M intersection N is singleton 0, and again it is easy to prove this by using this result: Z belongs to M if and only Pz equals to Z. So Z belongs to M intersection N. Consider the argument which we are writing. If Z belongs to M intersection N, then Z belongs to M and Z belongs to N. This implies, use the same result, P is projection. So this implies Pz is equal to Z by using this result, and Z belongs to N implies that Pz equals to 0. So this implies, combine these two, you can easily write that Z is equal to 0. Further, both are linear subspaces, so they clearly contain 0, and the only element or the only vector which both M and N can contain is 0. So if you take into account this fact that M and N contains 0, and further the only element which they can contain is 0 vector, we have the required result: M intersection N is equal to 0. So by combining all the four properties which we have proved, we can have our desired conclusion that B is direct sum of M and N. You can recall the properties which we have proved. First, we have proved that B is sum of M and N. Secondly, we have stated that M and N are linear subspaces. In third property, we proved that M and N are closed linear subspaces. And finally, we proved that their intersection is singleton 0. So by combining all this, we have our required result. Thank you.